Okay, so today we're going to take a look at some material stuff. So we're going to look at typical stress and strain curves for them, and then we're going to move on to look at unloading and loading curves for different materials. So to start off with, let's have a look at some stress strain graphs. So I'm just going to look at a typical one, then I'm going to look at how for different materials this graph is going to look different depending on the different properties the material has. So first of all, let's identify some of the key features on this graph here. Now, the two dots here on the left, I'm going to come back to later on because it's one of the key points I want to emphasize. So I'm just going to leave these 2 points out for a second and come back to them later. So let's first of all have a look at this point here on the top of the first peak. This would be is what's called a yield point. Okay, so that's your first point actually, where as you as you stretch material more, so the strain increases, you actually get a sudden decrease in stress, and that happens because the material has yielded, and then what you will see is the drop off at that point there, and you actually have a second yield point down here. So when you reach the bottom here and it starts to go back up again, that's actually another yield point you have there. So it's key to know that both of those things are yield points. Other key part though is this one on the top of the second peak here. This is what's called the ultimate tensile stress. It's often abbreviated to UTS, so if in an exam question you might see UTS or something, this is what this stands for. It's basically the maximum possible stress that a material can have, and the stronger a material is, the higher the UTS is going to be. And the final point that you need to be aware of is this one at the end where the graph stops, and that is your breaking stress. It's starting to overlap there, but that's okay. So that's your breaking stress. This is the point where the material has actually had so much stress, it's been stretched so much that it can't take it anymore. That is your breaking stress. Okay, so those are the key areas to identify on the graph. And there's a couple of key things that I wanted to bring to your attention. And the first is, to calculate stress, what we need to do is take the force and divide it by the area over which you're actually applying that force. So what you need to do is actually, you need the area perpendicular to that force. So if I just do a little sketch diagram over on the right hand side. So imagine we've got a material. What we're looking for is the area perpendicular to that force. So we're looking for this area which is at 90 degrees to the force. Now it's possible, if they wanted to make an exam question a little bit more tricky, they could give you an area that's not perpendicular to the force, in which case you'd need to adjust the area so it was. So say for instance, I'll just draw a diagram at the top. So we had a sloping line like that, and you applied the force in that direction. So to be able to calculate what the area is in the perpendicular direction, obviously it would be you'd effectively get an adjusted area. By knowing what the angle was, you could work out what the area perpendicular to the force was. So for instance, you just take the area and you multiply it by the cosine of the angle, and that will tell you the area that was perpendicular. So that's something they could do if they wanted to make it really more difficult, if they really wanted to stretch the question. I've never seen that before in an exam question, but I just wanted to draw your attention because it's possible. Second key thing, strain has no units. Because we calculate strain and we use this symbol for strain, obviously it's your change in length divided by the original length, which you will see written as L0. So obviously so if we look at the units of that, we've got meters over meters, which obviously cancels out and you end up with no units. So if you're asked to calculate the strain of something, remember not to give any units because they'll probably have the mark scheme penalise for incorrect units. Okay, so to calculate the Young's modulus, first of all, obviously you need to apply your formula. So we use the symbol for stress, which is this symbol there, and obviously you divide it by the strain, which is obviously, as we saw before, is this symbol here. Now, key thing to remember, it only applies up to the limit of proportionality. There we go. So this only applies to the limit of proportionality. So what does that mean? Well, I said I'd come back to this later on. Your limit of proportionality is the point where your stress-strain graph stops being a straight line. Now, the one I've drawn on the left over here is a bit of a sketch, but this was the point intended to be the point at which it stops being a straight line, and that's your limit proportionality. So you can only calculate the Young's modulus, so if you have a look on the left-hand side, on this section of the graph here, while it remains a straight line, and for some materials this is an incredibly short section, and actually the Young's modulus isn't really a significant thing to calculate for that material. But things like metals and stronger materials, it's actually a very useful method of doing calculations. So you can only do it on this section of the graph if you want to calculate Young's modulus. So I said I was going to come back to the limit of proportionality and the elastic limit. Now, there's a key difference between those 2 points, because a lot of people get them jumbled up or think they're the same thing, but they're not. Okay, so the limit of proportionality is the point at which your stress-strain curve stops being a straight line. So I've marked that over here with this black line. So that's this first red blob that you come to on the graph, because the graph from that point on is then curved. Okay, so that's your limit of proportionality. Now, your elastic limit is the point at which the material can't be returned to its original shape. So you've stretched it by a certain amount and you've gone past the elastic limit. That material cannot go back to its original shape and it's permanently deformed. But those two numbers are sometimes, for some materials, they'll be exactly the same. But for a lot of materials, they're actually not. For this material we have on the left-hand side here, your elastic limit is this second red blob you encounter. So there's actually a difference between the limit of proportionality, which was this first blob, and the elastic limit. And I just wanted to draw your attention because they're not necessarily the same thing, and that's an important difference. Okay, so I said I was going to have a look at some examples of different types of materials, and there's several key properties that you need to think about when you're looking at a graph and trying to work out what material it is, or trying to draw a graph of a material. So the first thing you need to know about a material is its strength, because this tells you where your UTS, or your ultimate tensile strength, is going to go on your graph. Because if you know a material is stronger than another one, you know its graph will have to go above that other one. The next thing you know is you need to know whether it's brittle or if it's ductile. Okay, so what do I mean by that? So a brittle material is one that you'll stretch the material, so you're increasing the strain, and what you'll find is that it will reach its yield point and then it will break really quickly. So it has no real plastic region on that. So that's a brittle material, so it won't have a plastic region, so you'll reach your yield point and then bam, it will break. Okay, and I'll show you an example of that in a minute when we're looking at example graphs. So those are the two sort of key properties we're looking for, whether a material is strong and whether it's brittle or ductile, and that sort of dictates what the graph looks like. So let's have a quick sketch of something we've seen already. So we've already seen a graph that goes something like this, okay? And that is a typical graph of a metal, but more specifically it's ones for using in construction, because this is quite a strong one. So I'm going to say this one is steel here. So you've got quite a sizable plastic region. So when I say plastic region, what I mean is basically the point beyond the yield point here. So you've got quite a bit of spread along here after it's gone past the yield point where the material is actually still not broken. So that's, it's got a fair plastic region. So it's not a brittle material. It's got a bit of ductility to it. Okay, so let's have a look at a brittle material. So when we say that, we're talking about something like, or I don't know, let's go for glass, okay? So you'd still get, with something like glass, you'd still get this region like this. And then, all of a sudden, you'd reach the yield point, bam, it's broken. So let's mark our yield point in here again. So in this, you can see we've got a really, really small plastic region here before it broke. So this is the feature you can identify a brittle material from. So hang on, let me just label this. So this is glass, which most of you will know is a brittle material, which is why we use like plastic and stuff for rulers, whereas they used to use glass, as it says on it, oh, it doesn't shatter. And like that's because it's not the plastic isn't so much a brittle material, but that's not too important. But never mind, just a fun fact. So this is your glass. So as like I said, got a small plastic region here, indicates that it's very brittle material. Other key thing, if we look at the ultimate tensile stress of your steel, which is up here, you see it's much higher than it is for glass. Okay, so your steel is a much stronger material than glass. I think that's most of you would know that, but it's worth pointing out. Okay, so let's draw a final one. Let's draw something that's really ductile. So let's go with something like this. So a ductile material will look like this. An example of this would be, again, it's another type of metal, but like something you might use for making wires and that sort of thing. So we're talking about your coppers and those sorts of wires we use for making, those sorts of materials used for making wires. Sorry, get a bit jumbled up there. Now, key points for this one. You can see we reach its yield point somewhere around here. We've got this long region, so you've got this graph is really long and stretched out, which means that even when it's gone past the yield point, still hasn't broken. And like actually, in actual fact, this graph would probably continue for quite a way over here, just to emphasize the difference between it and steel. So you finally reach its breaking point somewhere here. So you've got this really long stretched out part, which is showing it that even though it's gone past the yield point, it still hasn't broken. Like it's still just stretching and stretching and stretching and not breaking. And that's the characteristic of basically not something that's not brittle, of something that's actually very ductile. And it's actually going to be more ductile than a construction type material like steel, because that's why we use it for things like wires, because it can take the stretching without fracturing, and that's a really useful thing. So those are some typical graphs of materials, and depending on the use of a material, you'd look for different characteristics from this graph. So say in a question you asked, we need a material to be used as a construction material, like in buildings and something, you're going to want a graph that looks something like this one at the top, with this long region where we've got that you haven't reached the limit of proportionality and a very high ultimate tensile stress. If you want something to use for wires or something where it's going to be stretched a lot and you don't want it to fracture, you're going to want a ductile material, so something more like this one here. And obviously we don't pick glass for its strength or its ductility, we pick it because it's see-through. So obviously if you have a question that says, or sketch a graph of a brittle one, you want this really small plastic region up here. Okay. So we talked a bit earlier about the elastic limit for materials, and that actually comes really into play when we're looking at loading and unloading curves. Because if, when you're stretching it, you do not reach the elastic limit, that tells you that the load extension graph is going to start at the origin, go up, and then it's going to come back all the way through the origin again if you don't reach the elastic limit. However, if you do reach the elastic limit and you go beyond it, you know that that material is now in the plastic deformation zone. So that tells you that the material is going to be permanently deformed, so permanently stretched. So that means that it's not going to come back through the origin for this graph. And that's an important thing when we're talking about loading and unloading curves, okay? So let's first of all have a look at metals. So in this case, if we stretch a metal, we'll have something like this, and it'll go like this. Okay, and I'm going to mark on here the elastic limit, okay? So we're going to stretch it beyond the elastic limit. Now I've written over here match gradient, and that's important because I've seen an exam question on this topic. Okay, so if you were to draw the graph when it was then unloading, so let's mark this. This is your loading graph. If you were drawing it when it's unloading, I've said over here match gradient, and what that means is that your line back needs to be a very similar gradient to the one for loading. So if I were to do this, I'm going to sketch this, but this should be a straight line. That's pretty wonky, it's not the greatest line. What I'm trying to indicate here is that the gradient of your unloading line should be similar to the gradient of the line when it was loading in the when it was in the proportional section. So you should end up with a straight line, and the key thing obviously is because you went beyond the elastic limit up here, you're going to hit the x-axis at the non-zero point. So it's been permanently stretched, and that's how you show the material's been permanently stretched. However, say for instance we only stretched it to somewhere on this section before you hit the elastic limit. What would happen in that situation is it wouldn't be permanently deformed, so your line would just come back along the same line and you go back through 0, 0. Now that's important because one of the things when we're looking at loading and unloading curves is we want to know the amount of work done to load it and the amount of work we get out when we're unloading it, because sometimes there might be a difference, so there's a loss of energy, and sometimes they might end up being the same number. So let's look at the first example, we've gone beyond the elastic limit here, and then we've come back down to this here. Now, the amount of energy or the work done is obviously the area under your graph. So first of all, let's look at the amount of work done to load it up. So if we just sketch that where that is, so the amount of work we've done to load it up is basically all of the area to the left of the blue line that's under the graph. Okay. Now what about the work we get out of it when it unloads? Well, that'll be the area under the new line. So I'll just shade that area in there. That'll be this area here. So what you see is if you go beyond the elastic limit, you actually get some loss of energy because you don't get nearly as much work done out of it as you do when you stretch it, and that's a key point to note. So if you go beyond the elastic limit, you actually start to get less work done out of it than the work you put in, and that's all to do with the fact that you've caused a permanent deformation of material, and it requires energy to do that. So you get less work out than you do in. Okay, so that's an important feature of that. So we've looked at our metal graph now. So let's take a look at something a little different. So the next thing we need to look at is the graph of rubber. And the thing we obviously know about rubber is that it's really stretchy and it will often return straight back to its original length when you stretch it. So when we look at rubber, we don't really tend to think about it going past its yield point because you'd have to stretch it so much to get to that point. It's not really important. However, a key thing you might not know about rubber is its limit of proportionality is incredibly low, so we basically never have this region of proportionality. It's always a curvy line. So if you look at its loading curve, what it does is it looks something like this. Okay. So then, but when we unload rubber, what we get is actually something like this. And there's a couple of key features. So I'll just mark what's going on. Notice we haven't gone past the limit of elasticity because we said with rubber we're never really going to consider that because it's such a long extension to reach it. So obviously the unloading curve has to come back through the origin because it's not been permanently deformed. Okay, first key point. We've got an incredibly low limit of proportionality because obviously this graph at pretty much no point is proportional, so we've got a very low limit of proportionality. And the second key thing is that, or third, sorry, I'll make it the third one. We've got this here. And obviously before, when we looked at the metal, we talked about the amount of work done. And obviously, if this one on the top's loading, and this one on the top unloading. We're actually getting a small amount of work out of it, if we look at the area, than we did the work we've put in to stretch it. And you're like, well, we haven't gone past the elastic limit, what's going on there? And the thing with a material like rubber is it actually, some of the work you put in stretching is actually transferred to internal energy in that material. So you actually get, I'm not going to say energy loss, but some energy is transferred in a non-useful way to you, so you don't get quite as much energy back out of the material, which is why you get this curve coming below the original one, but as I said before, the key point comes back through the origin. So if you're asked to sketch rubber, what they'll be looking for is it comes back through the origin, and that you've got this line below the upper line to show that some energy is transferred to internal energy. Okay, so the last one we're going to look at is, as you can see on the right hand side, polythene. And again, what I've done is I've written match gradient, because that's an important thing here. So first of all, let's sketch the loading curve of polythene. Actually, it looks a bit like the one for rubber. But the key difference between polythene and rubber is you reach the yield point pretty quickly when you're talking about polythene. So if you go into your kitchen and find, I don't know, some polythene or cling film or something, if you stretch it, you pretty quickly realise that it doesn't actually go back to its original length because you've actually gone past the yield point of that. That's our loading curve here. But obviously if we've gone past the yield point, we know that it's going to be permanently stretched. And what we find when we do the unloading curve is we get something a little bit like that. And I've written on the right hand side match gradient, because if you look at the gradient when it's proportional over here, you can see that that's roughly, or I've tried to make it roughly the same as the gradient of your unloading curve. And that's a key thing to look for. If you've gone past the yield point for the material, you get the unloading curve being roughly parallel to your gradient when it was proportional, and that's a key thing to look for. And obviously, as you can see here, when it comes back, it's now permanently extended, so it's gone into the plastic deformation zone. And there's a key thing you might be to know is a material like polythene, you're going to reach the elastic limit very quickly, so you're almost certainly going to go past the yield point. So your graph will end up looking something like this. And just one final point when we're looking at these graphs. Obviously, I said to calculate the work done, you're going to need to think about basically the area underneath graphs to work it out. And a lot of people struggle with, well, how do I on earth do I calculate the area under this sort of graph, which is all wonky and curved? And there's not a especially good way of doing it, and I think the answer kind of baffles more mathematically minded people who think this is a very approximate way of doing this. But obviously this would be done on graph paper, so if we draw some lines in from our graph paper, I think you would probably find you had much finer graph paper on it. And what you actually do is you go, well, there's 1 square, 2 squares, 3 squares, there's about 4, 5, 6, 7. If we add these two together, I reckon that gives you 8. If I add those two together, that gives you 9. And I'd say that's about a half. It's about 9.5 squares. So then you work out, well, what's the area of 1 square in work done? And then you multiply by the number of squares, and that gives you the work done. And it is as simple as doing these counting squares, working out what each square represents, and then that will give you the answer for the work done. And it really is just as simple as that. There's no real complex maths way of doing it. I mean, you could, for those of you obviously who've gone a bit further, you could use some of your different rules for calculating or approximating areas. So we're thinking about trapezium rules and stuff. But that's really overcomplicating, and what the examiner was actually looking for you to do is go, how many squares are there? What does the area of 1 square represent? Boom, what's the work done? And that's all they're looking for that one.